So while every optimization problem can't be done exactly the same way, here are some guidelines for helpful things in doing optimization problems. If you follow these guidelines, you can make it a little simpler to figure out what you're doing with your problem and how you're finishing it out as an extrema problem. So the first thing that you want to do is you just want to figure out what quantity you're trying to maximize or minimize. So what quantity and whether you're trying to maximize or minimize it. Seems simple, but that's the starting point. All right, figure out what the variables are. If you can draw a picture, that would be helpful, but you won't always be able to do that. But put in as many variables as you need. Then you want to identify your objective function. Remember, the objective function was that quantity we're trying to maximize or minimize as a function of possibly several of your variables. So don't worry if there's more than one variable in there. We're going to take care of that. So then what we're going to do is we're going to look for any constraints or relationships amongst the variables. All right, something has to be there that's not allowing us just to use as big of values as we want or as small of values as we want. So we look for that and identify that. Make some equations out of it. Then we use those constraints or those relationships to reduce the objective function to a function of one variable. And we should note any domain restrictions because there's got to be some restriction here on the values that we're allowed. All right. Finally, we solve this an extrema problem. Like we've done before, we try and find max and mins. We can try and find relative max and mins and then reason whether they would make absolute max or mins. And that's how we go about it. So let's take a look at another example. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters. What dimensions require the least amount of fencing if no fencing is needed along the river? Okay. So let's see what we're doing. Basic idea. What are we trying to do? You can say it in words first. We're trying to minimize the amount of fencing. All right, whatever that means right now. I'm going to call that amount of fencing capital F. All right. So what are our variables? Well, again, we're trying to build a fence, so we have some river. Let's call that the river. And we're trying to put a square fence in an area around the river. So like this, okay? And the idea is we don't have to put any fence. Let me make that actually a different color. So let's do this. So we don't actually have to put any fencing along the river, so that changes it a little bit. So again, we have some variables that we can pick, and let's again just call it X and Y and call it L and W if you want, or whatever, it doesn't matter. So based on this, I have to think about how I want to get an equation for my fencing. So in this case, the fencing is really going to be the length of the fencing here. So for the fencing, I'm going to have these two sides of length X, so 2X, and then one side of length Y. Okay, so there I have my objective equation, right? And the only issue is it has more than one variable in it, but let's look for some constraints. All right, so what does the problem tell us? The pasture must contain 180,000 square meters. Okay, so that means I'm looking at some area. So the area of this rectangle in here is supposed to be 180,000. That would mean that XY has to be 180,000. Or in other words, Y has to be 180,000 over X. I could have done it the other way around, but it doesn't matter too much. I could have done X in terms of Y. All right, and let's see if there's any domain issues here. Well, we're not going to want, again, any lengths to be 0 or negative. So the smallest x could be would be just a little bit bigger than 0. And technically, in this case, we could send it towards infinity, because the only thing that's going to happen is as x gets a lot bigger, y is going to have to get tiny. So is it likely that x is going to be 20 million and y is going to be 180,000 over 20 million? No, but it is possible in the framework of this problem. So at this point, I have my objective equation and I have a nice constraint, and what I can do is I can put them together to get a function, the objective function, into one variable. And so what I'm going to do is just do f is 2x plus replace y by 180,000 over x, and that's my new objective function. And so my problem really becomes maximize f, which is now just a function of x, 2x plus 180,000 over x on 0, infinity. So I've made it into just an extrema problem. And to do that, that's the whole take a derivative, chart the derivative, etc. So that's what I'm going to do. I'm going to take f prime of x, which would be 2 from 2x, the derivative, and the derivative of 180,000 over x would be minus 180,000 over x squared. All right, and I'm going to ask, when is the derivative equal to 0? When is the derivative undefined? When the original function was defined? Well, if I take 2 minus 180,000 over x squared and set it equal to 0, then I would get 2 is 180,000 over x squared. I would get x squared then is 90,000. X is then plus or minus 300. But again, we're not going to use negatives here, especially considering our domain. And so we get x is 300. So now I want to see, what does that mean? Well, again, I'm going to draw my f prime chart. Now, I'm going to start again open at 0. I am going to go off to infinity, because that was my domain here. So, and I'm going to put 300 in there. Let me go back to my derivative, which is this. If I plug a small number, so I plug 1 in there, I get 2 minus 180,000. That's definitely negative. Oh, you know what I did incorrectly here? Hold on one second. We were trying to minimize the amount of fencing. So I just noticed something. Not maximize, minimize. We would have picked that up later, but good thing I fixed that now. All right, so we're trying to minimize this. So if I put a number bigger than 300 in, so if I put a number bigger than 300 in the denominator there, I'm going to get a huge number there, which means 180,000 over that number is going to be tiny. So 2 minus that number is going to be positive. All right, that means that I was decreasing before and increasing after. All right, in other words, f was decreasing here, f was increasing here. That gives me a relative minimum at 300 something. Okay, and I could figure that out by putting that into the formula up there for f of x. And if you do that, I believe you should get 1200 out of that. So then I reasoned to myself, okay, well, it's a relative minimum, but it was always decreasing before and always increasing after. So this relative min has to be my absolute min, and that's exactly what I'm looking for. So I'm looking for an x of 300, and y was 180,000 over x. So 180,000 over 300, which is going to give you 600. So in this case, we would need x equals 300 meters, I believe we were in. Y is 600 meters. Notice that in this one, we don't actually get a square. Now, if you go back, now that's because we didn't need any fencing along the river. So that changed the problem from before. Because we don't need that other side, we actually get our optimal situation when we have the rectangle of 300 by 600. So the other thing to notice is this was a slightly different problem. Similar to the first problem, but slightly different. In this one, our objective function was based on the perimeter, and our area was our constraint. In the previous one, our objective was the area, and our perimeter was the constraint. So you can have lots of different varieties of this